Hi everyone, let's talk about section 14.8, Divergence theorem. So we call that for in R2, we have the Green's theorem, we have circulation form, and the flux form. And then the circulation form, the idea we can extend to R3 and we get the Stokes theorem. Okay, so for the flux form, we can extend some idea into R3. Okay, so let me compare here. So in R2, the picture is like we have curve C. This is the region R, and the flux measure how much vector field is going across the curve, right? Well, the divergence is like we measure how much vector field flowing out near the points, right? Flowing out. Okay, then you can see here it match. Well, but in R3, so instead of a curve, we cannot say the vector field go across a curve. That's not defined. But we can talk about the vector field go across a surface. So you can think about let's say that's the easiest example. We can think about a ball, right? A ball is a surface. Then how much vector field going across the ball? That is the flux interval, flux surface interval. And that also measures how much vector field flowing out from the point, right? Okay, so here, flux and divergence. What is the relationship between flux and divergence? Yeah, imagine as a small closed surface enter at the point x, y, z with a small volume change of v. Then the divergence is like the limit of the change of v equal to 0. We measure the flux integral over the change of v. Okay, if S is very, very small with the volume change of v, then the flux interval is approximately equals to the divergence times change of v, okay? So here we have the divergence theorem. Let S be a smooth oriented surface, and let's say the orientation is outwards, okay? Because it's a closed surface, then there's only two orientations, either outwards or inwards. Let E be a connected and simply connected 3D region enclosed by S. Okay, simply connected means no holes. So it's inside, it's like a solid. Okay, no holes. And let F be a field whose components are differentiable inside the solid E. Then the flux interval, okay, the flux interval equals the triple integral of the divergence dv. Okay, so where n is the unit vector, the unit hours normal vector on S. Intuitively, let F represent the velocity field of a fluid that's flowing in some region. The divergence of F at a given point describes the strength of the source or sink there. And the divergence theorem says that the following two things are equal. First, the rate at which the fluids flow out across the boundary surface S. Second, the sum of the source minus the sinks throughout the interior region E. Okay? So let's do some examples. Let F be the vector field x cubed, y cubed, z cubed. Let E be the solid that is inside the unit sphere. And above the cone, z equals square root of x squared plus y squared. Find the outward flux of F across S, where S is the boundary of E. So let's draw some picture. So we have a unit sphere, right? So that is 1. And the cone is like that. Okay, so we want to find, let E is the solid inside the unit sphere and above the cone. Okay, so that is this region. So far, so good, everybody? Okay. And you can see, well, this guy, to calculate the surface integral is kind of hard because the top one is the sphere, the bottom one is the cone, right? And so it's more complicated. Maybe it's easier to compute the triple integral of this region, okay? And now let's see. Okay. So we can say by divergence theorem. Okay, our flux across the region S equals our triple integral on this solid. This is the yellow solid E, and we have the divergence. Okay, del dot F dV. Okay, what is the divergence? Well, that is, let's say, FGH Fx plus Gy plus Hz. Fx 3x squared, Gy 3y squared, Hz 3z squared. Okay, and so let's continue. So this guy is then the triple integral on this region. This is 3x squared plus 3y squared plus 3z squared dV. Well, look at this region. It's great to use the spherical coordinates. Okay, right? Because it's the sphere. So use spherical coordinates. And do you still remember what's spherical coordinate? We have rho, phi, and theta. And rho is from 0 to 1, right? How about phi? Well, look at this angle. So phi is the drop down angle, right? But at this point, if we cut it like this, okay, at this point, this is pi over 4. So phi is from 0 to pi over 4, and theta is from 0 to 2 pi. So far, so good, everybody? Okay. And because they are all constants, the order doesn't really matter. And here, x squared, y squared, z squared adding together, this is just rho squared. And what's dV? What's the volume differential? That's rho squared sine phi d rho d phi d theta. And rho is from 0 to 1, phi is from 0 to pi over 4, theta is from 0 to 2 pi. Okay, let's do the integrate with respect to rho. This is rho to the 4th. Integral of rho to the 4 is rho to the 5 over 5, right? And we have sine phi, and rho from 0 to 1 d phi d theta. Okay, evaluate from 0 to 1, we plug in 1, we get 1/5 minus 0, so we can move 1/5 outside. And then we have sine phi d theta. Okay, and what is that? Well, integral of sine phi is minus cosine phi from 0 to pi over 4 d theta. Well, because this guy has no theta, you know, it's like a constant, so it's just like multiply our answer by 2 pi, right? And when we plug in, we get cosine pi over 4, minus become plus cosine 0. Well, that's 6 pi over 5. Cosine 0 is 1, minus cosine pi over 4 is root 2 over 2. So this is our answer. So far, so good, everybody? Okay. Yeah, it's much easier than calculate the flux integral because we have two surfaces involved. The top one is the sphere, some portion of the sphere, and the bottom one is the cone. So we had to do both, and wow, that's a lot of work. Okay, let's continue. So here, let S be the unit sphere and find the outward flux. And usually, we use the divergence theorem to help us to calculate the flux using the triple integrals on the solids inside the surface. Okay, so here, well, unit sphere, right? Okay, so unit sphere, by divergence theorem, that is our ball, solid ball E, and we want to compute the divergence dV, right? Ooh, what is our divergence? FGH or Fx, Gy, Hz. And Fx, ooh, 1. Gy, 1. Hz, 0. So this is just 2. Oh, our integral is just triple integral of a constant number. I can pull out this constant number. Oh, this is just the volume of E. This is a ball. Yeah? What's the volume of a ball? That is 4/3 pi r squared. But sorry, pi r cubed. But r is 1, right? So the answer is 8/3 pi. Isn't it very easy? This is the triple integral, and we know the maybe we can say more by divergence theorem. Our flux integral on the surface S equals the triple integral on the solid E. Okay, nice. So far so good, everybody. Let's continue. Okay, so we have the F is the vector field and S is the sphere with radius A. Assume N is the outward normal vector. Evaluate both integrals of the divergence theorem. Okay, so we do need to evaluate the surface integral and the triple integral. Let's do the triple integral first because it's easier. So FGH, right? Divergence is Fx plus Gy plus Hz and 1, 1, 1. That's 3, right? And well, we know this is the ball with radius A, and so then the triple integral on the solid E, divergence is 3 dV. We can pull out the 3. Woo! Nice. This is just the volume of the ball. Well, volume of the ball is 4/3 pi r. R is A cubed. Ooh, so the answer is 4 pi A cubed. So far so good. This is a triple integral on the solid E. Okay, next, when we compute the flux integral, the surface integral, this is going to be the harder part. And let's see here. Okay, so first, what is the parameterization for the sphere? Okay, we use U be the drop down angle phi and let V be the angle theta. Okay, So then it's gonna be rho is a, that's constant. So a sine phi is u cosine v, and a sine u sine v, and a cosine u. Right? This is the parametrization. And was tu? Well, tu the root of okay, even though we have done this before, okay, it doesn't hurt to do it one more time with you, right? Just to review. The derivative is back to u, a cosine u cosine v, a cosine u sine v, minus a sine u, right? Tv, the root of cosine is minus sine minus a sine u sine v. The root of sine is cosine, a sine u cosine v. And that's 1. Okay. And what's tu cos tv? Okay. To save. So this is sometimes when I want to save some space and say some work, I just put I, j, k here, and imagine this is the determinant. Okay, so I component. Well, look at this guy. Cross multiply. We have a cosine u sine v minus mistake. This should be 0 because a cosine u has no v in it. So cross multiply, we just get this guy minus become positive. A squared sine u squared cosine v. Okay, and then we do minus j component of the determinant of these, 0 minus negative. Actually there are 4 minus together, it becomes positive. A squared sine u squared sine v, right? And then the k component is the determinant of this. Well, that's a squared sine u cosine v squared minus negative become plus a squared sine u cosine u and then sine v squared, right? Okay, yes, so this is how I do it. Then you can erase back the ijk. Save us some work too. Okay, so and can you see here we have a common factor, and sine v squared plus cosine v squared is 1. So this is just a squared sine u squared cosine v, a squared sine u squared sine v, and a squared sine u cosine u. Okay. Then continue. What is the flux integral? Well, on the sphere, the flux. Okay, so we use our f. Okay, so f. Let me do it slowly. So this is on the surface f dot n ds. So that is f xyz, or xyz axis a sine u cosine v, a sine u sine v, a cosine u, dot this guy, a square sine square u cosine v, a square sine u square sine v, and a square sine u cosine u d. Okay, u is phi. So actually the order doesn't matter. U is phi is from 0 to pi, and theta v goes from 0 to 2 pi. Okay. Let's continue. Okay. So maybe it looks scary, but we should be able to cancel all of them. Let's see how amazing it is. So a cube sine u cube, and then cosine v squared, right? And then we have a cube sine u cube sine v squared, and then we have a cube sine u cosine u squared du dv. Okay, do you see here we have common factor, and sine squared plus cosine squared is 1, so this together is just a cube sine u cube. And can you see in those two terms I can factor out a cube and sine u. Then we're left with sine u squared plus cosine u squared, and that is also 1. Awesome. I can move out the a cube, and then integral of sine u is minus cosine u. U goes from 0 to pi dv. Okay, a cube. So minus cosine pi is minus 1. And then minus cosine 0 is 1. So this is 2, right? 2a cube, and then integral of 1 with respect to v is just v. Evaluate from 0 to 2 pi. Well, this is just 2a cube times 2 pi. So our answer is 4 pi a cube. Is this the same? Yes. Oh, okay, great. It's the same. See? This is our answer. Yeah, sometimes when we have done a long problem, and then we're gonna pray in our hearts, please be the same, please be the same. Otherwise, we need to check, okay, which tiny steps we have make us mistake. Okay, luckily we get the same. So far so good, everybody. So this is the divergence theorem. Okay. Note, the divergence theorem applies directly as long as the surface S is closed and the components of the field F are differentiable. Sometimes this theorem can be used in an indirect way. Like, do you remember like the Green's theorem is only works for a closed curved path, but we can close off by adding a line segment to it, right? So here, same thing. The idea is to close off the surface by adding a surface, and then taking away the flux through each of the surface that we have added. Okay, so S equals, so we can add a surface. Usually we can add a flat disk, because a flat disk, the end is a constant. It's easier to calculate. Normal vector is a constant. Okay, so the flux interval on S, so this is the original flux through the surface S. It might be hard to compute from scratch. And the divergence theorem can be applied directly here because it is not closed. But after we adding a disk or a flat patch there, okay, now this surface B is closed. The divergence theorem can be used directly to find the flux. So we can calculate a triple integral on the solids that is bounded by this surface B. Okay, and then that's minus And then use that to subtract, so the surface we add is A. So A is not closed, we cannot use the divergence theorem, but usually this surface you add to it is like a disk. So it's much easier to compute the flux integral. Okay, and that's it for sessions 14.8. Now we have finished everything on Calculus 3. Okay, so if you have questions, feel free to ask me. Have a nice break. Bye.